All right, so we're back. We finished last time in the part one of my video looking at ranking those ionization energy elements. Now we're going to look at questions 13 and 14. So we're talking about reactivity. So the most reactive metal in the S block is located in which corner of the periodic table? So first thing to look at is where's that S block? In the S block are these first two columns on my periodic table, right? So we're just looking at these first two columns. And we want to know which one is the most reactive. So these are my metals, right? And remember, my metals get more reactive going down and to the left, so the easier it is for them to lose the valence electrons, which means that this lower left corner is going to be my most reactive metal. So I would say lower left. There we go. And then explain why in terms of valence electrons and atomic radius. So it gets more reactive going down because I'm adding energy levels, right? So I have a bigger atomic radius. Let me say I have a larger atomic radius. So it's farther away from the nucleus. Right, and the farther away it is from the nucleus, the easier it's going to be to remove it. And that's something we just know about ionization energy. The other part of this is the number of valence electrons that it has. So on the left side, they only have one, right? Column 1 has one valence electron, column 2 has 2. It's going to be easier for group 1 because they only have one. So not only does the larger atomic radius mean the electrons are farther away from the nucleus, but as I move to the left, I have less of those valence electrons, right? So it's easier to lose those valence electrons, making it more reactive. So that's why my bottom left-hand corner, francium, is my most reactive metal, because it is one valence electron 7 layers away from the nucleus. 14 then is going to be the exact opposite. So my non-metals increase going up and to the right. So that upper right-hand corner is where I'll find my most reactive non-metals. And here's why for that one. Pretty much the opposite reasons, right? So non-metals, we want to look at how easy is it for them to gain an electron. So, right, in terms of energy levels and atomic radius, those kind of go together in the same way. As I go up, I have less of those energy levels, which means my electrons get closer and closer to the nucleus. And I have more, I have more valence electrons as I move to the right. So if I have less energy levels and more valence electrons, meaning they're really tightly pulled to the nucleus, it's going to make those ones in the upper right-hand corner a lot easier to gain that electron. So these two are kind of just the exact opposite of one another. Metals increasing reactivity going down to the left because I have more energy levels and less valence electrons. My non-metals increase going up and to the right because I have less energy levels and more valence electrons. So it's easier for them to gain, easier for metals to lose. All right, reactivity is the tricky trend. But let's look at question 15 now. So we have successive ionization energies. What would happen if I took an electron off one by one? And we'll look, this is for sodium. And if we look at sodium on the periodic table, it's in this very first column, right? So it's in column or group number 1, which means it has one valence electron. And here's where that is. So you were told to drag that circle to that one valence electron. And that's this one dot way at the bottom left-hand corner. And the reason it's this electron is, one, it's the first one to be removed, right? Those outermost electrons are always the first to go. And it takes the least amount of energy because it's the farthest away from the nucleus. So it's kind of low down on this graph, right? It takes the lowest amount of energy. So those first couple electrons, whichever ones come before that first jump, are going to tell you your valence electrons, right? So if I had magnesium, I would see 2 dots down here. If I had aluminum, I would see 3 dots down here, and so on. So part B for question 15 says, as electrons are removed from sodium from the outside, so the third level, to the inside, the first level, the energy required increases. Why is that? So you want to think, well, what am I moving closer to? Why would it take me more energy to remove those inner electrons? And the reason really just being, they're closer to the nucleus, right? And the closer they are to the nucleus, the more of an attraction they have. So the harder they're going to be to pull off. So that's really it for why they're so hard to remove. They're just closer to that centerpiece. Last question for number 15 is explain why there's a large increase or a jump in energy required to remove the second electron and the 10th electron. So right here and right here. Hopefully you remember this when we talked about it in class. This just tells me when I'm jumping to a new energy level. So once I remove that valence electron, right, that one electron in the third level, well then I have to move into the second level. And I can take off those 8 electrons, then I have to jump to the first energy level, where I can remove those last 2 electrons. So that jump just tells me when I'm moving to either a new or inner energy level, right? So I went from the third to the second to the first. But that's all that jump is showing me when I'm moving to that new level. In these last 2 questions, I have part of the answer for 17 in here, but I will go over 18. I think we did this one as a group. So based on the data below, which element, X or Y, is silicon? All right, so here's what I know. I know that valence electrons take a small amount of energy, right? And then I have this big jump. So that's what I'm going to look for right here. I need to figure out how many valence electrons silicon has, and then see when that big jump is in my data. So silicon is right here, and it's in group number 14, which means it has 4 valence electrons. So that means I should be able to remove 4 electrons and then see a big jump when I get to the 5th. So if I look at element X, I see, okay, I have a little increase, little increase, a little increase, and then right after the 4th one, I have that big jump. So that kind of confirms what I need, right? After that 4th electron's removed, I see this jump because now I've moved into a new level. I've taken off those 4 valence electrons. So my claim would be that silicon is element X. My evidence, I'm just going to provide the numbers. So I went from this ionization energy to this ionization energy. And then putting that together in a reasoning, I could say, well, silicon has 4 valence electrons. So there's a big increase in ionization, and you can just say i.e. ionization energy from the 4th to the 5th. Right, and that's how I knew it. That's really all I looked at. There we go. So we'll do one more example, and it's one we did not do together. But it says, based on the data below, same type of question, which element, X or Y, is sulfur? First thing we're going to do, right, I'm just going to put sulfur is, because we want to know which one it is. I have to find out how many valence electrons sulfur has. So I'm going to jump to my periodic table and find sulfur, which is number 16, and it's in group number 16, which means it has 6 valence electrons. So that tells me I'm looking for a big jump in energy after the 6th electron is removed, i.e. 6. So I'm just going to look through them. X, all right, I have these kind of small jumps. Then there's a big jump, right, 6,000 to 21,000 after the 5th electron. So not really what I'm looking for, so I'll check out Y. Y has these small increases, and then I have this big jump from 8,000 to 27,000 after that 6th electron. So I know sulfur has 6 valence electrons, and that's when I see that jump happening. So my claim is that sulfur is going to be element Y. And my evidence, same thing, I'm just going to provide the data, right? I went from this at my 6th electron, so 8,940, to 27,000, just a casual jump in energy. And then my reasoning is going to sound very similar. I know that sulfur has 6 valence electrons, and there's a big increase in, well, I'll say ionization energy, or IE, from the 6th to the 7th. So that tells me that I've gone through 6 valence electrons, which were pretty easy to remove on the grand scheme of things, and then I had to move into a new energy level where it got a lot harder. All right, but you're just looking for at what point is that big jump in energy, and how many valence electrons do you have? And then it's pretty easy to figure out this kind of problem. But that is your whole periodic trends review guide. If you have any other questions from this part of it, or just things you want to ask, feel free to send me an email. We can set up a Google Meet and figure it out together.